In this problem, we are looking at a Wittig reaction and we are to propose mechanism for the transformation of the Wittig product to the aldehyde. So as the problem reads, this is a variant of a Wittig reaction which is useful in producing aldehydes. So draw the structure of the Wittig product going from the ketone here when it reacts with this Ylide, and then when the product forms, you are going to allow that to react with the acidified water to produce this aldehyde. So the first question is, draw the structure of the Wittig product when you react this ketone with the Ylide. So the ketone to Ylide, what is the product? And that product, when you treat that with acid and water, write a mechanism for the conversion of this product to the final product here. Okay, so go ahead, pause the video and make an attempt and then start when you're ready. So what is the product of this Wittig reaction? As we know, when you have a Wittig reaction, you're going to make an alkene from the ketone. So the alkene you're going to get is going to be those groups. So if you have a Wittig that looks like this, R prime and R, that's how the Wittig reaction is going to go. And also you have seen in the classroom that the Wittig can be also written in a zwitterionic form like that. So both are equally correct. So that's that. And the byproduct is going to be triphenyl phosphine oxide, as you know. Okay, so in this case again, that is a carbon, and here you have a hydrogen and a methoxy group instead of just an alkyl group, and the Wittig reaction would work just as fine as you see here. So one of the alkyl groups is a hydrogen and the other one is the methoxide that you see in this Ylide. Okay, so which means the structure of the Wittig is going to be a carbon-carbon double bond to another carbon. Here we have a hydrogen and here we have your OCH3, the methoxy group. Okay, and that is the answer to the first problem. Now we are trying to see, now we are going to see how you can convert this alkene product to the aldehyde product here. And when you treat this with acid and water, you are going to add a proton across the double bond, and the electrons are donated to the proton. The hydrogen can either go to that carbon over there or it can go to that carbon over there, but getting a positive charge on the carbon with the alkoxy group is going to be more favorable because of the assistance from the conjugatable lone pair from the oxygen. So the new hydrogen goes here, and this is where you will get a positive charge because you can write a resonance form which is using the lone pair to quench the positive charge. Excuse me. Okay, so this is the resonance form that will make this carbocation more stable. Therefore you will get the new hydrogen here and the positive charge on that carbon. Now when you have water in the medium, water is going to act as a nucleophile, and therefore you are going to get OCH3, right, and OH. So, and now as you can identify, this is a hemiacetal. You have a carbon, you have your gem diol or gem diol like structure where you have one alkoxy group and one hydroxy group, and that is essentially your hemiacetal. Okay, so now you know where the mechanism is going. So the H plus is going to, remember all these are also reversible steps, but if you have a lot of water, then the reaction is going to essentially become a net one-sided reaction. So when the next proton you have is going to protonate your alkoxy group, and it will convert that into a good leaving group. So those lone pairs are the ones that are used to act as a base. Okay, you get your, now this becomes a good leaving group, and you are going to get your carbon oxygen double bond, and and if you lose your proton, minus H plus. That is how you will get your aldehyde. So it's essentially an acetal giving you the hydrate, and the hydrate giving you the aldehyde. Essentially, that's what is going on there. So this is a good way to make a ketone into an aldehyde with an extra carbon. Okay.